Swayam Prabha. Digital India. Educated India.
Hello dear friends, welcome to this fifth lecture of module 4. In previous lectures we have discussed about aggregate, about crushed stone, about dimension stone, about pozzolan, about soil. In this lecture we are going to elaborate and address one of the critical problem caused by interaction of aggregate and cement. Friends, as you know, the concrete is made up of cement and aggregate, and engineering structure is based on bearing capacity of concrete, where the aggregate is going to play a very significant role concerned to strength of concrete. In this lecture, we are going to see about cement aggregate reaction. This cement aggregate reaction is also known as alkali aggregate. In this topic, we are going to elaborate about the concept of alkali aggregate reaction or cement aggregate reaction, then the classification of alkali aggregate reaction or cement aggregate reaction, then about deleterious aggregate, then mechanism of cement aggregate reaction, then impact, and finally control measures. Friends, here I try to attract your attention toward this figure. This figure is a foundation of a bridge. You can see carefully the high resolution figure. You can see number of crack network traverse through this foundation. If you see any concrete area more than 10-year-old, then you can see this type of feature. This type of features in concrete structure, this type of features you can map. It is a mappable features. These features can be mapped similar as we are performing in our geological mapping for any features and other. Similarly, here we can map this type of network of cracks and fractures, finer cracks and fractures you can see. This type of features we are going to observe in any building, in any bridge foundation, in any dam structures older than 10 years or more, 15 years, 20 years, 40 years, minimum 10 years required. It means initially these features was not present in concrete. With respect to time, suppose at time T1 it was not present, but gradually, slowly after a considerable time gap up to T2, means delta T is a log in tunes of 10 years, 15 years. In addition to this, if you see your concrete structure, mosaic concrete structure, floor of house older than 10 years, 20 years, 15 years, several places you can observe there is blowout of grains. Some of the mosaic structures showing very dirty type of appearance due to release of grains from the original concrete structure. Originally, at the time of formation or before 5 years, 4 years, 3 years, 2 years, the mosaic structure was beautiful, shining and others. After 10 years, more than 10 years, this started showing release of grains, blowout of grains from the concrete structure. This is a very severe problem, particularly related to stability. If such type of network or blowout of grains is started from the concrete structure, then the concrete is going to lose its bearing capacity and ultimately going to show failure of develop. In another words, we can say that loss of money, environmental problem, maybe safety hazards and others. This type of feature is nothing. It is a result of cement aggregate reaction in a span of time. Cement aggregate reaction. So, what is a cement aggregate reaction? Here I try to show this is cement. This cartoon is representing cement. This cartoon is representing aggregate. And this cartoon is representing water. Cement plus aggregate plus water is equal to concrete. Means for making of concrete we are going to mix cement, aggregate and water. Certain aggregates which technically we are considering as deleterious aggregate, if deleterious material present in aggregate, either in form of mineral, either in form of rock, corner or in any form, then this special type hazardous aggregate is going to react with cement in presence of water. You try to imagine this cement when we are going to mix water, then it becomes saturated. As per general concept, the cement is containing cations, mainly made up of carbonates containing Ca, Mg, Na, K and others. Minor ka, but Ca, Mg more, Ca more. When this alkali present in cement is going to interact with this aggregate in presence of water, then going to form some hazardous, some peculiar type of material at the peripheral area of grains, or fracture present either in concrete, either in aggregate, is going to lose its binding capacity or strength. This phenomena is recognized as cement aggregate reaction because the reaction occurs between the cement and aggregate. Water is present as evidence. Means presence of water is required, necessary, but the interaction between this alkali present in cement and aggregate. Therefore, this phenomena of cement aggregate reaction is also known as alkali aggregate reaction. This term become more popular in comparison to cement aggregate reaction. Alkali, here alkali present in cement is going to react with certain type of aggregates, deleterious aggregate, in presence of water during formation of concrete. Initially here, if we try to show a view of cement aggregate in concrete framework, we can see here the aggregate. Here we are going to utilize this figure, this aggregate, and surrounding to this paste, cement paste mixed with water, cement mixed with water, going to make paste, that is the cement paste, water present in cement paste. Here this deleterious aggregate is going to interact the alkali component present in paste in presence of water and going to react, ultimately producing features which we have already. A single crack can damage a big building or big fort after long duration of time. Such structures present in concrete and our major engineering structure like gravity dam, other retaining walls, bridge. Many important national structures are nationally important structure made up of concrete to ensure the stability, safety of the developed structure in interest of society. Now, first we are going to see this concept was based on observations. The peoples have started observing the development of crack network, blowout of grains from the mosaic, blowout of the grains, aggregate from the concrete structure, etc. As we have already discussed, certain constituent in aggregate can react harmfully with alkali hydroxide due to presence of water in concrete. Here we are going to discuss it simply. In this stage we can say that the reaction between aggregate and alkali is known as cement aggregate reaction or alkali aggregate reaction. This alkali aggregate reaction can be classified in two broad categories: alkali silica reaction and alkali carbonate reaction. Alkali silica reaction is a more effective because the varieties of aggregates belongs to igneous rock, metamorphic rock, sedimentary rocks, which mainly fall in silica containing category. However, limited limestone deposits is going to show less impact of alkali carbonate reaction. So now what is alkali silica reaction? Alkali silica reaction is a very simple reaction. The silica present in aggregate, if some distorted form, then there is alkali silica reaction. Developed by aggregate containing reactive silica mineral, amorphous mineral, cryptocrystalline mineral and deformed quartz. The amorphous variety containing silica and deformed variety containing silica are prone to alkali aggregate reaction or cement aggregate reaction. However, in case of alkali carbonate reaction, the presence of dolomite is a very problematic. If we are considering limestone as aggregate for concrete road or aggregate for the dam, selection of limestone sometimes also takes some dolomitic limestone. There is a presence of dolomite. Because dolomite is also a carbonate, magnesium carbonate, limestone, calcium carbonate. In nature, the calcium magnesium carbonate system is going to associate or provide dolomitic limestone, dolostone, various varieties which are prone to contain dolomite. If the limestone is containing some dolomitic component, used as aggregate of concrete by mixing the aggregate in cement with cement in presence of water, then this dolomite is going to interact with the alkali present in cement and going to cause such type of hazardous reaction. So one by one we are going to discuss. First, alkali silica reaction, which is more in impact. How alkali silica reaction is going to perform? Very simple. Here I try to take the same example here. This is aggregate containing amorphous silica or deformed silica, and this is the cement paste. This Si containing an alkali present in cement. So first, alkali present in cement going to interact with water and going to make alkali hydroxide. Alkali hydroxide, how? The alkali plus water in very initial stage. If we are going to divide in different steps, then we can say that, here I try to take this cartoon for help. This is aggregate, alkali A present in cement. This A is going to interact with the H2O present in paste. This A plus H2O is going to produce A hydroxide. This A hydroxide then going to attack on this silica containing aggregate. This silica containing aggregate, here alkali hydroxide going to attack on silica containing aggregate, and as per result in second step, as per result of this reaction, there is a formation of reactive alkali silica. This alkali silica gel have tendency of expansion in its volume. When there is any, here you can see this zone is a full of alkali silica gel, and alkali silica gel have tendency of the expansion. So if alkali silica gel present here, going to enhance this peripheral zone. If alkali silica gel, because fluid in nature, maybe fill this crack. So here this crack is a filling expansion. Where this alkali silica aggregate is available, at that point the concrete is a filling expansion inside. Due to expansion, what happens here I try to show with this very simple example. This is aggregate, suppose there is a formation of alkali silica gel at the periphery area, as well as if crack present inside, then inside this crack also. Beside this, some if space available in paste, then the alkali silica gel also move toward this space in concrete. Suppose point A, point B, point C, point D, point E. Point A is experiencing expansion, point B is experiencing expansion, point C, point D, point E. The framework is the same. Boundaries are not going to allow expansion or adjustment. Inside there is expansion, then what happens? Due to expansion, there is a development of expansion-induced stress. Expansion-induced stress. This expansion-induced stress, because the material is going to adjust, everything living or non-living, if under stress, then going to adjust with applied stress or stress working on its body. Then for readjustment of this expansion induced stresses, there is a development of cracks in concrete structure. These cracks are nothing, these cracks are alkali aggregate induced expansion in volume, resulted stress and adjustment of the concrete is going to provide some fracture, cracks and other. It means there is a development of such cracks and fractures to adjust with the developed stress due to alkali silica reaction. The amount of gel formed in concrete depends on, first thing, the quantity of silica containing aggregate, amount and type of silica aggregate, and number of aggregates containing such hazardous silica, amorphous nature or deformed nature. Then the alkali present in cement, and the main thing we are more concerned about the alkali hydroxide. So alkali hydroxide concentration in cement paste, and the availability of the moisture R1. Among these three, if we are going to cut anything, then there is no alkali silica reaction, and we will utilize this concept in our discussion concerned to control measures. Next type we are having, first we are going to complete ASR, then we are going to discuss about carbonate. The ASR form a gel that swell as it draw water from the surrounding cement paste. In absorbing water, the gels can induce pressure, expansion and cracking of the aggregate as well as surrounding paste, and resulting fracture or cracking or deterioration of strength of concrete. The alkali silica gel will fill the microcracks region both within the aggregate and concrete, and continuous availability of moisture or water to the concrete causes enlargement and extension of such microcracks in form of fractures and fissures, fractures and fracture network, and finally going to result reduction in strength of concrete or bearing capacity of concrete. If we are going to decide about most reactive substances, then the most reactive substances we are having opal, we are having chalcedony, we are having certain form of quartz which is deleterious in nature, then cristobalite and deformed quartz. It means deformed quartz means the quartz associated with metamorphic or tectonically deformed zone. In microscope, if we are observing undulose extension, it means the quartz is deformed in nature. So going to avoid in selection of aggregate, if aggregate is showing quartz grains as undulose extension, then such type of aggregate may be problematic in this direction. These amorphous silica containing materials we are having in different type of rock like opaline chert, we have rich opaline, then chalcedony chert, then siliceous limestone and siliceous dolomitic limestone or dolo limestone. These are particularly for alkali silica reaction, in short form ASR, alkali silica reaction. This if we are getting this aggregate or using this aggregate belonging to opaline chert, chalcedony chert, siliceous limestone, siliceous dolomite, then it is a problematic. How we are going, next aspect we are going to discuss, how we are going to identify potentially reactive aggregate. So identification of potentially reactive aggregate. This, as we have already discussed, the structure based on or concept based on observations and experience, the field performance history of structure in service. In majority of the cases, the structures more than 15 years is susceptible to such type of features. But it started 10 years, but we can see reach in 15 years. Different tests can be conducted for initially screening and evaluating potentially alkali reactivity aggregate or silica containing aggregate. The problem is very severe because it is going to reduce the strength of concrete, and whole engineering structure is based on bearing capacity of concrete. The improper selection of aggregate may cause such type of hazardous problems, loss of money, loss of time, delayed in project completion, and maybe some accident and so on. Very simple, we are going to pinpoint three steps. One is either we are going to reduce the alkali in cement, either we are going to reduce the availability of water if fortunately or unfortunately some silica, reactive silica containing material is available in aggregate. Then we are going to either block the availability of moisture, either going to reduce the alkali. Therefore, the use of low alkali Portland cement less than 0.6% equivalent Na2O is recommended for such type of suspected aggregate use. If low alkali cement is not available in any case, the total alkali content can be reduced by replacing a part of high alkali cement with supplementary cementitious material, as we have already discussed, means addition of pozzolan is going to help. And pozzolan we are going to use as a industrial pozzolan fly ash or ground blast furnace slag or silica fume or use of blended cement, etc. Another thing, wash beach sand and gravel with sweet water to ensure that the total alkali content from the cement and aggregate can be reduced, and as per recommendation, concrete does not exceed 3 kg per m3. Control of excess of water is also helpful. Replacing 25 to 30% of the reactive sand gravel aggregate with crushed limestone is also known by the limestone sweetening or simply sweetening. So sweetening process is going to retard or control up to some level about the ASR. Then utilization of the silica fume 5S, as we have already discussed. And next aspect, what are the parameters is going to affect the ASR? So water, aggregate selection means quality problem, quality control related problem. Another is alkali carbonate reaction. The alkali carbonate reaction is effective in aggregate belonging to limestone but containing some partial part of dolomite. If dolomite is present, then the alkali present, here I again try to explain with help of this cartoon. This aggregate if belonging to dolomite, then the alkali present in cement first interacting with the water present in cement paste, making alkali hydroxide. This alkali hydroxide going to interact with the dolomite. In case of Si containing aggregate, when there is a formation of gel, this gel is recognized as or belonging to silanol group. Silanol group material has susceptibility in expansion in volume. But in case of this carbonate aggregate, there is a formation of brucite. When this carbonate is going to react, suppose this dolomitic MgCO3 going to interact with the alkali hydroxide. Due to this, there is a formation of brucite, and brucite has tendency of expansion in volume. So in ASR, in case of alkali silica reaction, Silanol had tendency of expansion. In case of the alkali carbonate reaction, the brucite formation of brucite have tendency of expansion. Due to expansion in balloon, there is again development of the stress induced fracture. The influencing factor to the alkali carbonate reaction is mainly clay content or insoluble residue content in range of if in range of 5% to 25%, and if we are going to see the presence of dolomite where the calcite to dolomite ratio is 1:1, then there is a problem of ACR, alkali carbonate reaction. A small size of discrete dolomitic crystal also is going to create some problem, going to influence. How we are going to control this ACR? By selecting suitable quarry to avoid reactive aggregate containing dolomite. Blend aggregate with more limestone to reduce the quantity of the dolomite. In this way we are going to control ACR. Limit aggregate size to smallest practical size. In this way we are going to control ACR. Friends, this cement aggregate reaction is related to our engineering geological planning, design and success stories, and this alkali aggregate reaction or cement aggregate reaction is a very problematic with respect to time, going to influence the future of engineering project. This type of aspects we have collected and you can study in any engineering book, in material available on website and others. Only concept we have elaborated. So the helping book is Gangopadhyay's Engineering Geology, published in Oxford publication, ranging from page 1 to 549. Then the Engineering Geology written by Bell in 2007, the thick book, and the Kasavalu NC 2016 textbook of engineering geology. This is not very helpful but supporting. Waltham T 2018 Foundation of Engineering Geology also partially supporting. Friends, if we are trying to conclude our discussion, then we can say that the cement aggregate reaction is also known as alkali aggregate reaction, because here alkali is going to participate in such reaction. This is a two types: alkali silica reaction, which is in short form ASR, and alkali carbonate reaction, which is in short form ACR. The impact of alkali ASR, alkali silica reaction is more in comparison to ACR, maybe due to availability of the aggregate more containing silica. And this phenomena is a deteriorating concrete and hence concrete engineering structures in long run, and the reduction in alkali component of cement, blocking access of water, moisture and mixing of pozzolans are some of control measures to this problem, and going to save money as well as some control on the environmental issues also, etc. Dear friends, in this class we have discussed about one of the critical problem hazardous to stability of engineering structures like cement aggregate reaction or alkali aggregate reaction. The control measures of alkali aggregate reaction is necessary to save the future of developed engineering structures involving the concrete material. Thank you very much.